Hello, this is part 4 of the chapter 2 lecture. In this part, we are going to talk about nuclear stability and try to make some sense about what makes a nucleus stable, what makes an atom or stable. All right. So if you go back to part 2 of this chapter, where what we discussed is subatomic particles. Neutrons and protons are present in tiny area called nucleus, and outside you have electrons revolves around, right? So we said that tiny area, right? Let's focus on the tiny area because we said that there are positively charged particles inside, but they were squished together in the tiny area. So it is useful to know let's say, what is the density of the tiny area? What is the radius of the nucleus? And how dense they were packed inside in comparison to regular atoms? And see if it is useful to make any predictions on the stability of overall stability of the elements in the periodic table. All right. So as we just discussed again, nucleus is the small portion of the total volume of an atom. And stability of the nucleus, atomic nucleus, can be related to density because the nucleus contains most of the atom. Outside, it doesn't have any atom. So let's look into a hypothetical case of an atom with 30 protons and 30 neutrons. And let's try to identify what would be the density of its nucleus and compare it with density of an atom. And see if we can compare these two and say, like, is it small or big, something like that. So let's take an example of an atom with 30 protons and 30 neutrons, and radius of an atom with 30 protons and 30 neutrons is the radius of the nucleus of the atom with 30 protons is 5 times 10 to the power of -3 picometers. And if you try to convert them into centimeters by using the picometer and meter and centimeter conversion factors, you got 5 times 10 to the power of -13 centimeters. So we know the density equation, which is mass over volume. So mass of an atom with 30 protons is 1 times 10 to the power of -22 grams. And now, because the radius is in a circular form, the volume is going to be 4 by third pi r3, and r we already know. So if you plug it in, if you solve for it, the density of a nucleus with 30 protons is going to be 2 times 10 to the power of -14, which is saying that it is about quadrillion times bigger than 2. So really dense in just 1 centimeter cube volume. So much mass it can acquire. That's what it is saying. In comparison to this huge density, if you compare the density of any known highest density element, which is iridium element has the highest density of all the available elements, and it has only the density of just 22.6 grams per centimeter cube. See the huge difference between density of an atom versus density of the nucleus. So what these numbers are telling us that is that approximately the density of the nucleus is about 1 trillion times larger than the density of an atom. Imagine that. The density of the tiny area in the atom is about 1 trillion times larger than the density of an atom. So whatever we are packing inside must have strong reason to stick inside. Otherwise, in that small tiny area, you couldn't fit much of them unless there is a strong reason for it. And if there is, something that they couldn't work out, the nucleus cannot be stable anymore. So let's discuss a couple scenarios and come to conclusion on why some elements are highly stable and why some elements are radioactive, which is unstable on its own. Okay, so here are a few examples, or here is the generalization of all the elements in the periodic table in terms of protons and neutrons. Again, we already discussed that number of protons is only constant for an element, but number of neutrons is not. An element with the same protons can have many other isotopes with a different number of neutrons. So in these cases, it comes up to be, you can have number of protons and number of neutrons ratio varies. So depending on those numbers, if the protons are even or odd, we come to this overall conclusion that there are more stable nucleus with these magical numbers of 2, 8, 20, 50, 82, or 126 protons or neutrons in it. Whenever you find this magical number, those nucleus are somehow they were stable. Again, these are all happening because what is happening inside of nucleus is when you try to put them together. Let me just take a breath. According to Coulomb's law, we already know that like charges repel, opposite charges attracts. In addition to that, while neutrons helping the repulsions, minimization of repulsions, you will also have short-range attractions between both the positively charged particles inside. So the attractions between these positively charged protons is also causing the stability of the nucleus. So only if the repulsions between the protons is greater than the short-range attractions between these protons inside the nucleus, you will have an unstable nucleus. Let me repeat this because this is very important to understand the nucleus stability. So when you put all of these protons inside, you will also have the short-range attractions between these powerful magnetic protons. They will experience these short-range attractions between them because of the proximity they were put it in, right? Even though they were similar charges, because they were highly packed, like remember, in just 1 centimeter cube of volume, you will put like quadrillion times of gram mass in it. So because of that, they will experience short-range attractions between protons. So if those short-range attractions between the protons is greater than the repulsions they experience each other, then nucleus, we call it as unstable, or in other words, it will emit radiation, which means spontaneously spits out the subatomic particles like electrons or neutrons or protons. However, if the short-range attractions between protons and the nucleus is greater than the repulsions between the protons and the nucleus, then you have a stable nuclei. So when we say these are magical numbers, at these times, the probability is that short-range attractions between those protons are greater. That's why they were stable with those magical numbers. And also it is happening that more stable nuclei are occurring when you have even number of protons and the neutrons present, because that is where you have largest number of stable isotopes. And also any element that has greater than 83 protons shown to be unstable, which means their repulsions between proton and proton are greater than the short-range attractions between proton and proton. So we call any element with greater than 82 atomic number as radioactive because they spontaneously emits radiation by spitting out these subatomic particles. And in addition to that, all isotopes of titanium and polonium are also radioactive. So these are other cases. Odd and odd is not a great combination apparently because only 4 stable isotopes are present. But odd and even and odd about on par with each other. They have equal number of stable isotopes, about 50. But the magical number seems to be when you have even number of protons and even number of neutrons, their short-range attractions are greater between them. So they were keeping the nucleus more stable. All right. Now let me put all of this into one graph and explain this graph. This is the most useful graph that you could use to understand the stability of the nucleus. So what we are discussing is here, we started with discussing the density of nucleus. We said it is about trillion times larger than a typical atom size. Because it is so dense, there is an issue of keeping all the protons inside of the nucleus, especially because they have same charges. So the nucleus has to rely on proton-proton short-range attractions to keep the nucleus stable. But if those short-range attractions are dominated by the repulsions between proton and proton positive charge, so they repel and destroy the nucleus or emits radiation. So during this process, neutrons also will play a key role in minimizing the repulsions between protons. So as the atom size getting larger, as you have more protons inside the nucleus, you would also need to use more neutrons inside to minimize those repulsions. That's why you see this trend of number of protons from 1 until 82 we are discussing. the ratio between proton to neutron is deviating from 1-to-1 ratio. This is the line that showing that this would be a hypothetical 1-to-1 ratio between neutron and proton. However, it is deviating from it greatly as you started having more number of protons in the nucleus. Initially, you typically have a close to 1:1 ratio between neutron and proton here when the atomic number is close to 10. But as you keep on adding more protons to an element, you make bigger elements. Those elements shown to have greater neutron to proton ratio, because here you can see that for an element with 36 protons, you have the ratio of 1:3 rather than simply 1:1. As you go all the way to the top until the last stable nuclei of lead-82, you happen to have 1:5:1 ratio of neutron to proton. So this explains the nuclear stability, and all the elements that are present here in the belt are stable nucleus, and any element that is present below or above are not stable. So naturally, all the radioactive nuclei of the elements are not part of this nuclear belt of stability. So any element that is found in this are found to be stable isotopes of element. Any element that is not found in this belt of stability are found to be unstable isotopes of that particular element. That's all you need to know about nuclear stability.